This lecture is related to a lab where we are studying the frequency response of physical systems, and so I'll review a little bit about how, what a frequency response is, why we want to use it, and also very briefly about how we derive them theoretically from a model. These are concepts and methods that you might have covered in a course such as the Dynamic Systems and Controls lecture. So frequency response is basically what it is. You're putting in an input, and think of it as a sinusoidal input. And if this is a linear system, the nice thing about it is that the output will also be a sine wave, but there'll be changes, right? So you'll have, let's say you have the input and you know the input because you're controlling that, and it's some U naught. And remember, this could be an electrical signal, it could be a physical signal, something that you're putting into a system, a force or a pressure. So you know U naught, and you want to know what is the output. And the output here could be the response of the system. It could be a motion, it could be a volume, a temperature, whatever it is that you're studying. But note that there's going to be a change in the amplitude, there's going to be a change in phase. And what you might have studied in your dynamic systems classes is the concept of Bode plots. And Bode plots basically tell you, how do these guys vary as you change the frequency, right? Here's the forcing frequency. The forcing frequency is the same. If this is a linear system, if you put in, an input with a certain frequency, the output's going to be the same frequency, just again change in amplitude and phase. And I'm illustrating that here with this little figure. The input is the blue, and you can see there's some phase. You might put it in starting, say, at 0 seconds here. There's going to be some phi here. Think about like a lot of times, sinusoids are really hard to find in real systems. So the nice thing about it, if this is a linear system, remember any signal, remember your Fourier concepts, any signal can be, if it's periodic, right, can be composed of many sinusoids. So this really, these principles hold for any system that you can kind of approximate as linear, and if you can understand how the input and output relate through a representation of some kind of what we call a frequency response function, which is what we'll talk about, an FRF, then that tells you how to relate the input and output. So it's a very useful concept, and I'll show you some examples of how it's used. We'll also talk in a related video on how we can, in here, I'll briefly review how you might have already, studied deriving them from a model theoretically, but how do we measure them? And I'll talk about that in a related video on experimental measurements. So the frequency response from, one way to get it is from a transfer function, which for a linear system is defined as sometimes in different ways, but it's strictly, at least mathematically, it's the Laplace transform, and this is what is shown here. You're putting, let's say your output is y of t. If you take the Laplace transform, then you get a y of s. You strictly don't have to use a Laplace transform. It's really just kind of the output over the input. If you want to think of it really simply, if you're not, say you can't remember what Laplace transforms are, that's fine. It's really, the transfer function is a ratio of what is the output over the input. It just happens that it is a function of this S complex operator. And I'm going to show you, if in fact, if you can think about it in a certain way, there's different domains that we like to think about systems. We often think in the time domain, but the S domain is the Laplace transform, but there's also a frequency domain. And all of these can be related in different ways, right? So if you want to go from the time domain to the S domain, you can use a Laplace transform. If you want to go from a time domain to the frequency domain, I would use that as a little script f, and that's Fourier transform, right? So Fourier transform, and this is Laplace, can relate the time and frequency domain. It's a useful thing. And so these guys are also related in this little triad. And I'll show you that the way we can do that in shorthand is we can just make S equal to j omega here. And by having the transfer function that you've learned how to derive already using different methods, right? Either from system equations, going to state space, deriving the transfer function, or using the Laplace transform, or sometimes we use what we call impedance methods. Once you have a g of s, just by making s equal to j omega in this function, you can basically derive this complex function, which we call as FRF. And that's now in the frequency domain. And it's, the basis is this representation between these different domains that we work in dynamic systems. Note that the g of j omega, again, is a complex number. We can also write that in polar notation. And here's where it brings out that, you've got a magnitude or amplitude function, and you've also got some phase, right? So those are the functions that we sometimes call Bode plots or Bode functions, right? This amplitude ratio strictly, this is not just the amplitude, it's the amplitude ratio, and also the phase. And that's what relates those functions. And so by finding this theoretically from, if you have the g of s, which you can get again from a model, then you can derive this if you have a model of the system and all the parameters. If you don't, then you want to run some experiments, and then you can find these experimentally, as I'll talk about in a related video. So what are these guys good for? Well, straight away you can do, we often talk about running simulations in the time domain. You put an input into a system, steps or ramps or even more complex inputs, and we look at the response over time. A lot of times, though, you want to know, how does it respond over frequency? Well, simply stated, if you have, let's say you had amplitude functions, and they maybe look like this, and then so this might be your g, and this might be your phase, and it might look like that, and then there's some forcing frequency over here. What you can do now is, hey, it tells you if I'm forcing it somewhere at omega, let's say f here, this tells me, basically what the amplitude ratio will be there. Remember that the g is the amplitude, the magnitude, the peak, if you like, over the input. So if I have this guy and I have this guy, I can solve for that guy. Right? So you can estimate, you can predict how a system will respond. And this is why, right, you've seen, for cases like, resonance, if this guy has a peak, over here, and you force it close to that peak, right, we worry about that. Oh, it's going to be amplified in that region. Or if it's way out here, it's going to be, so we talk about this being an amplification and this being, right, an attenuation, because maybe it's below a certain level, right? So this is what frequency response functions can give you, the ability to predict not only the amplitude but also the phase, like how much will the signal, the output, lag the input, right? And so that's a really big part of doing dynamic analysis, because sometimes maybe the representation you have is only a frequency response function, or maybe the context of your work is in the frequency domain. And again, we can derive these theoretically, or we can get them experimentally. Just a really quick example of a very classic first order system. You recall, you might have hopefully seen this in dynamic systems. This is something that might look in time domain like this, but you could have derived the transfer function. You make s equal to, you go into the s domain, you get the transfer function, and then you make s equal to j omega, and you get the frequency response function. And now you can plot these by just solving for the magnitude and the phase, right? And a little bit of review of how to get magnitude and phase of complex numbers can help. For example, to get the phase of this complex number, you take the arctangent of the numerator minus the arctangent of the denominator, and well, this is the this is the inverse tangent of the imaginary part, which is 0, over the real part, which is 1. So that's why you have a 0 there. But then the denominator has, real values have tau omega over 1. So that's why you're left with that. So again, a lot of times, you might have already done this in your class. You've reviewed that. But just remember, these are very tangible ways to derive these. A lot of times, when you're actually going to get, quote, Bode plots or frequency response functions, you might do this by hand, and I'll show you really quick in a second how to do this in Python without having to derive these if it gets more complicated. Okay, but deriving some of these simple ones can kind of give you some insight. Okay. When we plot them, be mindful, we don't plot necessarily, sometimes we might, but we don't plot G of j omega. We sometimes plot what is called a decibel of that. So we take the log base 10, multiply it by 20, and those are the units that we plot in. That's why when you see Bode plots, you see the magnitude here. This will be plotted in dBs, and the phase will typically be plotted not in radians but in degrees. That's just kind of historical. The omega, you might either see omega here in radians per second, or you might actually see frequency in hertz. So just be mindful of that, and depending on the application or what you're reading, just look at those different units, because they sometimes are used differently depending on the context, again, of a problem. Very quick example, here's a high-pass filter, right, where you have maybe a capacitor and you have a resistor, and this, and you know, high-pass filter, by its context, you know that, oh, at low frequencies, it's going to look something like, it's going to be attenuating at low frequencies, and then it's going to pass the high frequency. So maybe you're trying to take the low frequency part out of a system and only pass what's at the higher frequencies. And so you might build a circuit like this. This could also be another physical system that has these characteristics. Again, I just show you an example for you to review, and the derivation of that. I'll let you go over that if you like. But what I wanted to show is how you can code this up, you know, kind of, let's say, hard coded in Python. So let's say you wanted to compute the, and right here is where I got the, you know, I went ahead and computed the G of j omega, the magnitude, and also the phase function is down here. And this just shows you how to compute that, you know, without using any special functions except what's built in. And it just shows you how to, in particular, I wanted to show you how, you know, you create some zeros here to fill in. Again, a little lesson on Python. You create a complex G of S just to emphasize that it's a complex number. And then you just step through this and you can compute these. I've posted on the course website this example. Let me bring that up. And what I did is I actually ran a few little experiments, and I only measured the magnitude. And so you can see here I've got at different frequencies. Here are actually some specific resistance and capacitor values. I measured the magnitude. I didn't measure the phase. I was using a multimeter, and I believe these are all in RMS. So I'm measuring RMS values for different frequencies. And I kept the voltage constant at 6.81, and I varied the frequency, and then I measured the output. And this is not magnitude ratio; it's actually the explicit, you know, RMS voltage. So then to compute it, I take the peak, right, the output, or peak, or I can't remember if it's peak or RMS, divided by the input, same magnitude, right, whatever metric you're using, whether it's RMS or peak, log base 10, 20, and then I plotted that against the theoretical one I just showed on those slides. And, you know, if you run this guy, and you can download this from the class website, it just shows you the code on how to do that. I want to just in contrast, it's coming up, so you can see pull this in here. There's the data, the circles, and then the theoretical. So this is something that we like to do in the lab if we have a model, or let's say we don't know what the model is, and we might want to adjust the black line. Here's the model. We might want to adjust it to fit the experimental data, and now that model has certain parameters, and you can sort of do what we call a little system identification. I'll talk about that when we're discussing the experimental part of the measurement of determination of frequency response functions. Okay, go back to slides. There are the results. I just also want to mention that you can also use Bode functions either in Python or in MATLAB. In Python, it's in the SciPy signal package, and this just shows a little snippet of that code. I've also uploaded a code for that into the Canvas page, but you can see here, the nice thing about this is that you only have to give it that, like you can define the numerator and denominator. And so you can see here's where you define, like in the numerator, there's a tau, right? S, and you see how it's in the second, it's in the, so like this is a tau S plus 0, right? So you have it in that element here, and 0 is the first element, right, or 0th element. And on the bottom you have tau S again, and then plus 1. So you can create your transfer function, numerator, denominator, and then you just pass it to this definition for a transfer function, numden, and then you just ask it, hey, signal, Bodhi, give me the magnitude and phase, and then you can plot those, right? A lot of examples online for how to use that, and that's really, practically speaking, how most people do it if you have these, you know, linear models in transfer function form. Also have posted another example, right, that you can look at, just a second order system. And let me just jump to, here it is. Another example here. Here's the numerator, denominator for you to look at, and I'll upload this code also to the Canvas page so you can see. And if you run this guy, right, you get a nice little classic second order response. Okay. So before I close, I just want to, like, so what is this good for? I wanted to recall for you, you know, that you've seen frequency response again in your 344 class. In the lab, we've seen it too in the context of sensors. This, we might also have it in the context of actuators, but also in how systems respond. So here's a nice example of accelerometer that we've talked about in this class. And if you have a calibration sheet sometimes, or we talked about bandwidth, and this shows the, what they call the sensitivity of this accelerometer, and note that it shows over a frequency range. And so this is the frequency response of the accelerometer. It tells you the sensitivity in millivolts, which is the output of the sensor, and the input is the acceleration in G's. You have 10 millivolts per G all the way out to, this is 100, so this is 200, this is a log scale. So it shows you that the bandwidth is out to 200 hertz. This is a seismic device, so we know that there's a resonance in here. It's because this is where it's rolling off, right? Because it's a second order system, so the damping is greater than 1, right? But if it was resonant, you would see a peak here. So where you want to use this accelerometer, and that's what the frequency response tells you in this context, is within this 200 hertz bandwidth, right? So when you would look at this accelerometer, they would tell you, hey, the bandwidth of this guy is 200 hertz. Where that specification comes from is from a frequency response function, right? I'll talk more about some other applications in the related video on experimental measurement.